Chapter 7, Unit 2. Let's talk about the shape, the central tendency, and the variability for the distribution of sample means. First off, we have to talk about the central limit theorem. This says that the central distribution of sample means for any sample size n will always have a mean of mu, which is equal to the population mean, and the standard deviation will be equal to standard deviation of the population over square root of n. And it will approach a normal distribution as n approaches infinity. So we're going to break this down a little bit. The larger n gets, the more like a normal curve the distribution of sample means will be. Okay? So you can see different distributions over here. The larger n gets, the more shaped like a normal curve it will become. By the time n equals 30, the distribution of sample means is almost perfectly normal. So the central limit theorem looks at the shape of the distribution, it looks at the central tendency when it talks about the mean, and it looks at the variability by looking at the standard deviation. So this distribution of sample means is almost perfectly normal if several things happen. First off, if the population from which the sample are selected is normal. Second off, if the number of scores n in each sample is relatively large, around 30 or more. With an n greater than 30, the distribution of sample means is almost normal regardless of the shape of the original population. And just keep in mind that many textbooks, if you take other classes, will say n greater than 20 here. Let's look at the expected value of m. The expected value of m states that the mean of all sample means is equal to the mean of the population, because we always expect the average of all sample means possible that you can take to always be equal to the population mean. So this means that you will always expect that m will equal mu. So expected value of m is always mu. So anytime you're asked the question of what is the expected value of m, the answer is always the population mean. Let's look at the standard error of m. So the standard deviation for the entire distribution of sample means actually has a name. It's called the standard error of m, and it uses the symbol standard deviation of m. Standard error is very similar to standard deviation. It describes variability. It describes how much difference is expected from each sample. So when you work on your homework and you have a question that asks how much difference is expected, you're going to calculate standard error of m. A small standard error means that the sample means are close together and are pretty similar. A large standard error means that the sample means are scattered over a wide range and there's big differences between the samples. So standard error also measures how well individual sample can represent an entire population. It provides a measure of how much distance is reasonable to expect between one sample mean and the overall mean or average of the sample means. Because m is equal to mu, standard error also shows how much distance to expect on average between a sample mean and a population mean. So keep that in mind when you do your homework when it asks for how much distance. You're going to compute standard error. So let's look at the equation for standard error. Typically, it's going to be written as standard deviation over square root of n. So the magnitude of standard error is determined by 1, the size of the sample, right? N is in the equation. 2, the standard deviation of the population. As sample size increases, standard error decreases, okay? Because if the denominator gets bigger and bigger, that means that the standard error is getting smaller. The law of large numbers says that the larger a sample, the more probable that the sample mean will be closer to the population mean. So basically, the larger n means less error. Let's talk about population standard deviation in comparison with standard error some more. So again, as we said before, if you have a sample size of n equals 1, the standard deviation would just equal the standard error. And as sample size n increases, the size of the standard error decreases. So the larger samples are more accurate, they have less error. So let's look at this graph. You'll notice that this is a problem based on a standard deviation of 10 for a population. So if you have one score in your sample, then you're going to have a standard error of 10. That's the first dot on your graph. But look what happens if you have 25 in your sample, then you have a standard error around 2, and so forth and so on. So the standard error kind of plateaus between 1 and 2, somewhere after 25 or 30. And again, this book says n greater than 30, and other books say n greater than 20. Let's look at the calculation. So if we had the same problem we were talking about, where the population standard deviation was 10, and we had a sample size of n equals 1 chosen from that population, if we calculated standard error, you can see the calculation there, standard deviation of 10 over square root of 1, which is the sample size. You get 10 for estimated standard error. Let's look at, we had a sample size of 16. You put 16 into the equation for n, and you'd get a standard error of 2.5. Notice if you went all the way up to a sample size of 100, you'd get an estimated standard error of 1. So the higher the sample size, the lower the standard error. Here's some different ways you might see the standard error equation written. And you'll probably see the first equation of standard deviation over square root of n mostly in this chapter. In later chapters, we're going to talk more about variance. So in which case you might see square root of the variance over square root of n, or square root of the variance over n. Any of these equations are perfectly acceptable for standard error. Let's look at an example. If samples are selected from a population that has a mean of 50 and a standard deviation of 12, then what is the standard error of the distribution of sample means for n equals 4 and for a sample size of n equals 16? So these are two separate problems. Let's look at n equals 4. If we were going to find the standard error for n equals 4, we'd put in what we know. We know standard deviation of 12. We know n equals 4, and you can solve, and your answer would be 6. So the standard error would be 6. Now let's repeat this for n equals 16, which is a larger number for n, which should give us a lower standard error. And it does. If you put 16 into the equation instead, you end up with a standard error of 3, which is about half the error. Let's look at a graph of the original population of IQ scores. It's the graph on the upper right. You were told that you had a mean of 100 and the standard deviation is 12, okay? And then here's some 16 random IQ scores selected from this population. And then let's say that of these samples that we looked at, n equals 16, we found an estimated standard error of 3. And remember that the estimated mean of the sample means is actually equal to the population mean, which is still 100. So the mean is still 100 for both graphs, okay, for the distribution of sample means and for the original population. What's different is that now on the original graph, you had a standard deviation of 12 that you graphed, and on the new graph, you have a standard error of 3. So when you use that, the graph becomes much smaller. It's less variable because standard error is much smaller than the standard deviation, so 3 is much smaller than 12, so your graph becomes much narrower for your sample. You don't have all those outlying scores that you would have in the original population. So it looks much narrower, so much less variability. Let's do some learning check problems. So pause the video, see if you can solve the problem. If a random sample, each with n equals 4 scores, is selected from a normal population with a mean of 90 and a standard deviation of 20, then what is the expected value of the mean for the distribution of sample means? Again, this problem you should just know immediately. There's no calculations. Once the expected value of the mean, it's just equal to the population mean. So your answer would be 90. Problem 2. If random samples, each with n equals 4 scores, are selected from a normal population with a mean of 80 and a standard deviation of 12, and the mean is calculated for each sample, then how much distance is expected on average between m and mu? So let's figure this out. If we're talking about how much difference is expected, That's talking about standard error. Okay, so the calculation for standard error would look like this. So you'd put the standard deviation of 12 over the square root of n. In this case, n is 4. You should get 6 for your estimated standard error, and that's your answer, B. 6 points are expected. Learning check problem 3. A sample of n equals 4 scores has a standard error of 24. What is the standard deviation of the population from which the sample was obtained? Well, first off, we're still going to use the standard error equation. The estimated standard error is equal to standard deviation over square root of n. We're just going to fill in what we know. We know the standard error is given as 24. We know n is given as 4, and we're going to solve for standard deviation of the population. So work the problem through, and you should end up with a standard deviation from the original population equal to 48.